Hello there, students. In today's video, I'll be discussing some test questions on the first law, thermodynamics. In the past, I already had tackled briefly one of the laws, and that was the zeroth law of thermodynamics, which simply describes what the natural tendency for thermal energy, uh, what direction it takes. We said that the flow of thermal energy transfer is always from a hot body, okay, to a cold body. So that was termed as zeroth law, thermodynamics, sometimes called the law of thermal equilibrium. In this video, I'll be discussing about the first law, okay? Exactly what is, or what do you mean by thermodynamics? Well, some books define it as the relationship between two processes of transferring energy. These are heat and work. So exactly how is heat related to work, or how is work related to heat? Which is easier to change? Is it easier to change, okay, work or mechanical energy into heat, or is it easier to change heat to work or mechanical energy? Okay, both processes actually describe the way energy is being transferred. When we say work, we are transferring the energy from one body to another, okay, by applying a force. And that force has to be in the direction of the displacement of the body on which the force is being applied. Okay. What about heat? Okay. The recent concept about heat, in fact, is that it is not a form of energy. What is it then? Heat is actually just a process of transferring energy from one body to another because of their temperature difference. Take note, the energy is transferred because there is a difference in temperature. Okay? And that is explained in the first, or in the zeroth law of thermodynamics. Heat flows from a hot body to a cooler body. But the amount of heat or energy that is being transferred is or remains constant. And the first law of thermodynamics specifically is saying that the amount of energy during the transfer always remains constant. It is just transform or change from one form to another, which is exactly the law of conservation of energy. First in our list of thermodynamic concepts is the term thermodynamic system. What is a thermodynamic system? All right. So when we say thermodynamic system, it is just any object that has the ability to exchange energy with its surrounding. So this object or objects may either absorb or liberate a certain amount of energy with its surrounding. A very good example is the case of popcorn kernels in a pot with a lid, right? We know that when the pot is placed on a stove, energy is added to the popcorn by conduction of heat. And as the popcorn pops and expands, work is being done, all right, on the lid, because the lid moves it, or the popping popcorn moves the lid through displacement. So there is work done, and the state of the popcorn changes in the process. right? So how do we know that there is a change in state of the popcorn? Because we know that the volume, temperature, and pressure of the popcorn do change during the popping. So what is the first law of thermodynamics? Actually, the first law of thermodynamics is just a restatement of the law of conservation of energy. But this time, we are going to relate three key concepts. All right? We have the internal energy, or to be more specific, the change in the internal energy of a system, and that is represented by delta U. All right? How it is related to another important concept, which is the value of the heat energy that is absorbed or that is emitted by the system, and of course W, which is the work done by the system or on the system. So we define the two parameters such as the initial value of the internal energy and the final value of the internal energy that is denoted here. Mu naught stands for the initial internal energy, and mu without a subscript is the final internal energy. It's quite difficult to exactly um, describe, much less to measure, okay, each of these values of internal energy. But the difference, or delta U, is the one that we are more interested about. So what is the equation for the first law of thermodynamics? It's simply equal to delta U, or that is final minus initial internal energy, is just equal to the amount of energy that is absorbed or that is liberated, that is denoted by capital Q. That is traditionally called the amount of heat, all right? The amount of heat that is gained or lost in the process, minus the amount of work done by the system or on the system. And if it is the amount of energy, thermal energy that is, that we are looking for, then we just transpose that equation, isolate big Q, and we will have the working formula, which is Q is equal to delta U plus work W. All right, and we also have certain sign conventions to follow. If the amount of heat big Q is positive, it simply means that the system is gaining heat, okay, gaining or absorbing, okay. And when it is negative, then we say that it is losing or it is liberating heat. Now, for the work done W, a positive W, okay, means that the work is being done by the system. Take note, by the system. But when the work W is treated as negative, or when it comes out negative in our computation, it simply means that the work done is on the system. we can illustrate the changes in the system's internal energy. Okay, we have some examples. But first, let us emphasize once again that the first law of thermodynamics can be stated as the change in internal energy being equal to the heat transferred and the work done. So in our diagram, we are given uh, this in letter A, 150 joules of heat, okay, is gained by the system or is absorbed by the system as indicated by an arrow representing Q directed into the system. Then at the same time, the system is doing work equal to 100 joules. So look at the arrow, it is pointing away from the system. And computing for delta U, all right, we have Q minus W, that is 150 joules minus 100 joules. So that gives us 50 joules, which is positive, all right? And the positive 50 joules of delta U simply means that the system has increased its internal energy by that much, all right? What if, in letter B, what if the system gives off or liberates, okay, 150 joules of heat, okay? Look at the arrow, it is directed away from the system. Then, okay, an outside source, all right, an outside agent is doing work on the system, labeled or represented by an arrow pointing into the system. And the work done by an outside factor is equal to 100 joules. So when we calculate for the change in internal energy of the system, we have negative 150 joules as the value for Q minus negative 100 joules for the work done on the system. So negative 150 minus 100 joules, that gives us negative 50 joules as the value for delta U. Okay? A negative delta U, okay, means that the internal energy of the system has been decreased, okay, by an amount of 50 joules. So that's the meaning of a negative delta U, a decrease in its internal energy. And lastly, for letter C, we have, again, the system absorbing an amount of 150 joules. Look at the arrow, it's pointing into the system. But at the same time, the same amount of work is done by the system. All right, the arrows or the arrow representing W is pointing away from the system. So we have a case where the amount of heat that is gained by the system is exactly equal to the amount of work that it does on its surrounding. So when we calculate for its delta U or change in internal energy, that is Q minus W, we will get positive 150 joules minus positive 150 joules, and therefore the delta U is just equal to 0. What does a 0 delta U mean? It simply means that the system, it is as if the system has not actually increased nor decreased its internal energy. That is the meaning of delta U being equal to 0. Although it's obvious that there was a process of gaining an amount of energy and doing work on its environment or surrounding. All right? It's just so happened that the value of the amount of heat absorbed and the amount of work that it does on its surrounding are equal. So the net effect is that its internal energy seems to remain constant. All right, so once again, we will emphasize the process of calculating for delta U based on the first law of thermodynamics. Here's another question, similar question. A system gains 1,500 joules of heat from its surroundings, and 2,200 joules of work is done by the system on the surroundings. All right, so Letter B question. The system also gains 1,500 joules of heat, but 2,200 joules of work is done on the system by the surroundings. So we are to determine the change in the internal energy of the system in each case A and B. All right. So to help us out in our analysis, we again have this illustration. The arrow that represents the amount of work done, all right, is shown. The direction of the arrow suggests that the work done is by the system, all right? And this is for letter A, or case letter A, and the heat, the direction of the arrow representing heat is directed into the system, so meaning it is absorbing, okay, heat. For letter B, the arrow representing the work done is directed into the system, so that means the surrounding is doing the work on the system, while the arrow representing heat is directed into the system as well. So, means that the system is absorbing or gaining heat. Alright, so our solution for the two cases, in case A, we take note that the heat absorbed or heat gained by the system is labeled here as positive 1,500 joules. And then for the work that it does, W is equal to positive 2,200 joules. And using the equation for determining delta U, all right, we substitute the value for Q, which is positive 1,500 joules, minus the value for the work done, which is positive 2,200 joules, and that gives us a delta U equal to negative 700 joules. And the negative simply means that the system has decreased, okay, decreased its internal energy by as much as 700 joules. So, what about in letter B? So, in letter B, the same amount of heat is absorbed by the system, okay, positive 1,500 joules. But instead of work done by the system, this time it is the surrounding doing the work, all right? A work that is of the same magnitude as the one earlier given in letter A, right? The surrounding is the one doing 2,200 joules of work. Hence, our label for W is negative, negative 2,200 joules. Again, because this work is done on the system by the surrounding. So, getting the delta U, we have Q minus W, or when you substitute positive 1,500 joules for the value of Q minus negative 2,200 joules for the work done on the system. And this gives us a delta U equal to positive 3,700 joules. Once again, the meaning of positive delta U is that its internal energy has been increased, okay, by as large as 3,700 joules. Okay, so if you notice in letter A compared to what we have in letter B, the change in the internal energy, okay, for letter A is that the system has decreased its internal energy, while in letter B, the system has gained or increased its internal energy. Okay, so why the difference? You can just again describe the way the work done. Is it by the system or on the system? And how is the amount of heat? Is it being liberated or is it being absorbed? So those two factors will determine whether or not the internal energy of the system should decrease or increase. Before we proceed to more sample problems, let's first talk about thermodynamic processes. Okay. First in the list is what we call isobaric process. Okay. So when you say isobaric, we mean a process that occurs at constant pressure, meaning the pressure labeled P is held constant, something that doesn't change. So the work done by the system, okay, which is labeled as capital W, of course, is just equal to the product of the pressure multiplied by the change in volume. So capital V stands for the volume of the given amount of uh, the system or substance, okay? Which also means that P is multiplied by the difference in the final volume, okay, and the initial volume. We expect that even at constant pressure, right, uh, the volume of the system somehow will change from V naught to a volume, final volume V. All right, so that is the meaning of this equation. Okay, if the work is done by the system, again, uh, where W, of course, is positive, it simply means that, okay, the system, for instance, if the system is a gas, we say that a positive work, W, uh, that the gas is expanding isobarically, right? Expanding isobarically, meaning there is an increase of its volume without a change in pressure, right? And the opposite of that is called isobaric compression, where the final volume is expected to be less than the initial volume, or V less than V naught. And in which case, we have a work done that is negative, okay? Meaning it is the surrounding or the environment doing the work on the system, right? And that is well illustrated in this diagram. The, uh, the diagram illustrates, okay, the two cases when uh, or before the event took place. We have here a case: the mass is maintaining its constant pressure. Okay, the mass inside the cylinder, right? The same pressure is applied on the given mass. Okay, so there is a piston, okay, here that prevents any possible leakage. If this is a gas, okay, the gas cannot just easily escape, okay, from this container because there's a piston that prevents that to happen. All right. So uh, from from this event to that event, okay, obviously this suggests that there is an increase in the volume, okay, from an initial volume to a bigger amount of V without changing the pressure, of course. We call this an isobaric expansion of the gas. All right, so next in the list of thermodynamic processes is what we call an isochoric process. Okay, one that occurs at constant volume. The volume of the system remains the same, okay, before and after uh, the event or process. So as illustrated here, okay, we have a sample of a substance, either solid, liquid, or gas, that is to be heated, okay, in a rigid meaning sturdy, hard, all right, chamber. All right, so while heating, we make it a point that the volume will be the same even if it is going to be heated. No change in the volume, hence that's what we call isochoric. All right, so while being heated, of course, we expect that the temperature of the substance will increase, and hence the pressure will also increase. Okay, an increase in temperature, okay, at a given initial pressure will result, okay, to an increase in temperature as well as in pressure. But, okay, the volume of the substance doesn't change at all, right? So even if pressure rises, okay, there will be no work done by the system. Why? Because uh, this vessel or this chamber is so hard that it cannot easily be moved, all right, by the heated substance. So no displacement, even if there is a force, no displacement, hence no work. It is zero. What is the purpose of the heat that is being absorbed by the substance if there is no work? All right. It simply means that in an isochoric process, the amount of heat that is absorbed only serves to change its internal energy. All right. As shown again by the first law, thermodynamics, if W is zero, therefore delta U will be equal to Q minus W. Since W is zero, therefore delta U is equal to Q. Any amount of heat that is gained by the system, okay, only makes the internal energy of the system increased. Or if in another case the the Q is negative, if the system liberates heat, okay, with no work done on it or by it whatsoever, then the delta U would mean a decrease in its internal energy. The third example of a thermodynamic process is what we call isothermal process, a process that takes place at constant temperature. So as shown in diagram letter A here, there is an amount of gas, initially 2 liters of gas, and this is inside this, uh, again, a chamber, all right, that is being heated slowly, all right, a very slow process of heating, whose initial temperature, of course, is given, say, for example, 300 Kelvin, all right, and even if there is an expansion going to happen, okay, as the gas is being heated, of course, we expect that the volume of the gas will increase, right? So from state 1 meaning the initial condition where the volume is, for example, 2 liters. Then it's being heated and changes to a state where the volume has been increased to 5 liters. Okay, but in the process of changing the volume, okay, the temperature is strictly held constant, hence the word isothermal, right? Now, because of the expansion of the gas, it is doing work on its surroundings, such as the piston. Okay, so there is work done, positive work of that, and then there is heat being absorbed by the system. So both W and Q are positive. That is what is illustrated in A. Both work and heat are positive, but the temperature is kept constant. Okay? And since the amount of heat absorbed is just equal to the amount of work done by the system, okay, each time that it absorbs certain amount of heat, okay, such amount of heat is just being used, okay, by the system to do work in pushing the piston. So we say that Q is equal to W. Therefore, as a result of that, the first law of thermodynamics tells us that there will be no change in the internal energy. Delta U, which is Q, okay, plus W, right? So it will be equal to 0, and a delta U that is equal to 0 is also indicated by no increase or decrease in temperature. Okay, we are going to show later that uh, the change in delta U is in fact uh, indicated by a change in temperature. Okay, how about in example B or in situation B? Okay, in situation B, we make sure that uh, the chamber or the container is well insulated. All right, and initially also the gas is only confined in one compartment whose volume is initially equal to 2 liters. In other words, the inside of this chamber is divided into two compartments. Okay, the first one, the lower compartment, is where the gas is confined. Okay, with a certain initial volume of 2 liters, and then the other compartment is kept what we call in a vacuum. There is nothing in here. No amount of gas is in the upper compartment. But it is simply, all right, the two compartments are just simply separated by this partition that is breakable, all right? The piston, I mean the two compartments inside, okay, are separated by a partition, but that can be broken, right? So again, because the chamber is well insulated, okay, uh, that is to make sure that the temperature of the system doesn't change. We keep it at 300 Kelvin, okay. That's why it's called isothermal. No change in temperature. But the moment the partition is broken, okay, when it breaks, what happens to the gas in the lower compartment? It starts to expand until the whole space inside is occupied by the gas, amounting to a volume of 5 liters. All right. So there is an increase in the volume from 2 liters to 5 liters. But then again, no change in temperature, no heat is absorbed or given up by the system because it is well insulated. All right. I mean the piston, I mean the chamber is well insulated. So likewise, no work is done by the system because the piston here is not going to be moved. All right. No no movement whatsoever of the piston. It doesn't rise. All right. As a result of the expansion of the gas. So sometimes they call this what we call a free expansion of a gas. In a free expansion of a gas, all right, uh, the volume is changed, but the temperature remains constant. No amount of heat is either absorbed or liberated, and hence no work is done by the system or on the system. And therefore, using the uh, first law of thermodynamics, we say that the delta U is simply equal to 0, since Q as well as W are both 0. We call this an isothermal process. Okay, that can happen in different ways, as shown in or illustrated in situation A as well as in situation B. The fourth example of a thermodynamic process is what we call an adiabatic process. Okay? Adiabatic simply means that no heat, okay, will flow into the system or out of the system. So Q is equal to 0. And the example in illustration B, which we described earlier, right, where the gas is inside this insulated chamber, okay, it is so insulated that we do not allow any amount of heat that is given off by the gas or any amount of heat that is taken from the outside. Okay, the term adiabatic, okay, simply means that Q is equal to 0. Now, the change in internal energy as a result of an adiabatic process, the change in internal energy delta U, okay, can be expressed, okay, using the formula that we are going to discuss in the next slide. Right? It goes like the internal energy U is equal to 3 halves times the number of moles denoted by small letter n times a constant, we call this the universal gas constant, and the Kelvin temperature. So 3 halves nRT is a conceptual definition of internal energy based on the ideal gas law, which we're going to discuss in the next slide. So given that, we can therefore, okay, express delta U in terms of 3 halves nR times the difference in temperature, T final minus T initial. And since there is no big Q is 0, our delta U expression, okay, in terms of the work done, W, can now be stated as W equals 3 halves nR multiplied by the initial temperature T naught minus T. Okay? So, uh, when is delta U negative? Right. Based on this formula, W, since W is positive, okay, in the expression T naught minus T, okay, if that T naught minus T is positive, all right, our delta U is negative, okay, and that would mean that the final temperature will be decreased. It will be lower than the initial temperature, all right. In other words, when a gas expands, okay, you will notice that the final temperature would be smaller than the initial temperature, all right. So we call it an adiabatic expansion of an ideal gas. Now, the opposite is what we call an adiabatic compression of an ideal gas. That is, if work W is negative, so that the initial temperature is less than the final temperature, meaning that the delta U is positive. Therefore, this is a case where the final temperature of the system or the gas is higher than the initial temperature. Okay, we call this an adiabatic compression. And the two cases are well illustrated. For example, if you're going to exhale, if you're going to exhale and you try to feel the temperature of your breath, okay, so you're going to feel the what do you call the breath as you exhale. You will notice that a few inches from your mouth, okay, when you exhale, you will notice that the temperature of your breath, okay, seems to become cooler from a distance of, say, uh, 4 or 5 inches away from your mouth. Okay, try that uh, to verify what I'm saying. And in the case of an adiabatic compression for an ideal gas, if you have a bicycle pump, for example, and if you're going to compress the gas by pumping the bicycle pump, okay, by pushing the piston up and down, you will notice that uh, the cylindrical container, okay, of a bicycle pump gets warmer, an indication that the temperature of the gas as it is being compressed, okay, the temperature is increasing. So those are the examples of this adiabatic expansion as well as adiabatic compression of an ideal gas. So we now talk about the ideal gas law. An ideal gas model for real gases, okay, that have sufficiently low densities. When we say low densities, we mean that we imagine the molecules of the gas not to interact with each other because they are so far apart, okay, and hence uh, very low density, right? If ever there are interactions, such interactions simply do happen when they collide, but the kind of collision involved is considered elastic. Okay, as we all know in the conservation of momentum and energy, we say that during elastic collision, okay, and that applies to the collision of molecules, okay, the amount of energy is conserved. So, the ideal gas law expresses the relationship between the variables absolute pressure, okay, the Kelvin temperature, the volume of the gas, and the number of moles of the gas. Okay, and we therefore state, okay, this equation that was uh, presented earlier, the product of the pressure times the volume, or P times V, is just equal to the product of N, the number of moles, times capital R, which is known as the universal gas constant, and the Kelvin temperature, okay, which can also be expressed in another way. Okay, we can also express the product PV as, or in terms of capital N, which means that we are talking about the number of molecules. All right, N, capital N, is different from small n. Small n represents the number of moles of a given sample of gas, while capital N is the number of molecules, and that is to be multiplied by another constant K, whose value is not the same as that of capital R. For capital R, the value is 8.31 joules per mole Kelvin, while K is also known as Boltzmann's constant, and that is equal to 1.38 times 10 to the negative 23 joules per Kelvin. Okay, so this is sometimes called the ideal gas law equation. You may use the formula in terms of the universal gas constant or in terms of uh, the formula which makes use of the Boltzmann's constant. You will get the same value for PV, or the PV actually means the work done by the system, okay, or on the system, depending on what the sign is. We will now discuss question number 2. The temperature of 3 moles of a monatomic ideal gas is reduced from T naught equals 540 Kelvin to a final temperature T equals 350 Kelvin by two different methods. In the first method, 5,500 joules of heat flows into the gas, whereas in the second method, 1,500 joules of heat flows into it. Now, in each case, we are to find letter A, the change in the internal energy, and letter B, the work done by the gas. So our solution for letter A, okay, we just make use of the formula for determining delta U in terms of the formula for or suggested earlier, 3 halves times the number of moles multiplied by the universal gas constant R, and the temperature difference, that is T minus T naught. Okay, that is equal to delta U. Now, substituting, of course, we have 3 halves times 3 moles multiplied by the constant, capital R, and the change in temperature from 350 Kelvin to from 540 Kelvin to 350 Kelvin. So 350 minus 540, doing your algebra, we will get this delta U equal to negative 7,100 joules. So the negative sign again means that the internal energy, the gas, has been decreased. All right, so for question letter B, all right, so since delta U, or the change in internal energy, is now known, and that the heat is given in each method, the work done for each method can now be calculated. For the first method, we just use the formula work is equal to Q minus delta U. Okay, that's rearranging the variables for the first law. We're looking for W. All right, so substituting, therefore, we have 5,500 joules for Q minus negative 700 joules, and that gives us the amount of work done, which is 12,600 joules. And that is in the first method. Notice that the work done is positive. All right, meaning the work is done by the system or by the gas, as also suggested in the question. Now, for the second method, the work, again using the same formula, is computed as 1,500 joules of Q, or heat, minus negative, all right, 1,700 joules, and we will get uh, an amount of work equal to 8,600 joules, obviously much less than the amount of work done by the gas in the first method. Okay, more work is done in the first method, okay, a lot bigger amount of joules compared to the second method. Okay, And that's precisely because of the amount of heat, okay, that was absorbed by the gas in each case. Okay? The big difference in the amount of heat absorbed by the gas, okay, explains why the amount of work, okay, that it does is also bigger, because uh, the change in internal energy, okay, is the same for both cases or for both methods. So we expect much bigger amount of work done, okay, by the gas in the first method, where the amount of heat that it absorbed was a lot bigger than what it did in the second method. We're down to our last question, number 3. A series of thermodynamic processes is shown in the pressure volume diagram as shown. Okay. In process AB, 150 joules of heat is added to the system, and in process BD, 600 joules of heat is added. So, in the graph of PV, okay, relationship between pressure and volume, point A represents the initial state of the system, okay, whose initial volume V naught is given as 2 times 10 to the negative 3 meter cube, and its initial pressure P naught is 3 times 10 to the 4th Pascal. So, the first process from A to B, okay, is actually an isochoric process where the volume doesn't change. Okay, only the pressure changes from uh, 3 to the 4th Pascal to 8 to the 4th Pascal. So that is process AB, and according to the problem, 150 joules of heat is added to the system. And then, in the process BD, okay, from point B to point D, that's represented by the blue arrow directed to the right, we're talking about an isobaric process, where the pressure at 8 times 10 to the 4th Pascal doesn't change. Okay, but the volume changes from V naught to V. So you're asked to find, or during that process, isobaric process BD, 600 joules of heat is added for a total of 150 joules and 600 joules or 750 joules of heat is added to the system as the system moves from state A to state B and to state D. We are asked to find the internal energy change in process AB, right? So during the isochoric process, what is the change in internal energy delta U? That's for letter A. For letter B, we are also asked to find the internal energy change in the process ABD. ABD, meaning the whole complete process from its initial state of A to its final state at D, but passing by the intermediate state B, ABD. So both questions A and B are asking for the delta U. All right, and in letter C, it's the total heat Q that we are going to calculate, but referring to the thermodynamic process ACD. Okay, ACD, meaning from point A to point C, which again is an isobaric process, and then from C to D, which is an isochoric process. Okay. We have to determine the total heat added. So how we are going to do that will be shown and explained in the next slide. In answering the first question, letter A, where we are looking for the internal energy delta or change in internal energy delta U along the path AB or process AB, okay, we take note of the fact that process AB is an isochoric process where the work done is equal to 0 because there is no change in volume. But the amount of heat absorbed by the system is given at 150 joules. So it follows that the change in its internal energy or delta UAB is also equal to that amount of heat absorbed UAB, which is 150 joules. For letter B, it's asking for the work done on the or work done by the system in changing from state A to state D, passing through the intermediate state B. Okay, first, we define the amount of work done in the process BD, which is an isobaric process whose determination of the work done is just equal to the product of the pressure, which is constant, multiplied by the change in the volume. Okay, we have this formula. WBD is equal to the product of the pressure multiplied by the change in the volume. All right, take note this is an isobaric process. So we use the value for the pressure that is constant, 8 times 10 to the 4th Pascal, multiplied by the change in the volume from V naught to V, okay? But we are getting the difference, final V minus initial V, so we have here 5 to the negative 3 meter cube minus 2 times 10 to the negative 3 meter cube, and we get this amount of work done for the isobaric process equal to 240 joules, okay? We therefore emphasize that the work done in the whole journey or the whole process in moving from the initial state A to the final state D, passing through the state B, is just equal to WABD, or the sum of the two works, WAB plus WBD. Since WAB is equal to 0, that gives us a value of the work done by the system also equal to 240 joules. For the last question, letter C, we first take note that the answer earlier we got for WABD, which is equal to 240 joules, can be used to determine the required answer in determining the change in internal energy along the path ACD. All right, ACD, the one represented by the red arrows. But we first take note that the total amount of the heat absorbed by the system amounting to 750 joules, that was determined by adding the two amounts of heat along the path AB plus the heat along the path BD. Okay, 150 joules plus 600 joules gives us 750 joules. So that is the total amount of heat absorbed by the system when we are considering the path ABD. So from that, and from the value of the work done, ABD, we can determine the change in internal energy delta UABD, which is just the difference, 750 joules minus 240 joules, or 510 joules. Okay, so what is significant about this delta U along that path ABD? It is because in answering the last question, which is finding the amount of heat, okay, absorbed by the system in changing from its initial state A to its final state D, okay, we take note of the fact that the change in the internal energy along that path ACD, we label that here as delta U ACD, is just equal to the amount of change in the internal energy, okay, from A to B to C to D, right, labeled here as delta U ABD, and that was earlier calculated to be 510 joules. Okay, why are they equal? It is because change in internal energy delta U is considered a function of state or a state function, which means that it is independent of the path taken. Okay, regardless of the kind of path. For example, from A, how do we go from A to D? Okay, we can pass from A to B and then to D, or we can pass through A to C and then to D. Notice that in those two paths, the initial state is just the initial states and the final states are just the same for both paths. That is the meaning of being a state function. So we make use of that concept where the delta U is considered path independent. Now, we are only left now with the problem of determining the work done, okay, from A to C. Okay, we first have to determine the work done by the system in moving from initial state A to initial state C. Okay, actually, what we are after is from A to C to D. But the fact that C to D is an isochoric process and the system will not be doing any work. So in our computation here, we just show the pressure, which is P naught, okay, that is 3 raised to the 4th Pascal multiplied by the change in the volume from 2 times 10 to the negative 3 meter cube to 5 times 10 to the negative 3 meter cube. Multiplying that, okay, we get a work done equal to 90 joules. Okay, so 90 joules is the work done as the system goes from its initial state A, passing through state C, and then moving on to final state D, 90 joules. And therefore, for our final computation to determine the amount of heat, okay, that is absorbed by the system in doing that process, okay, isobaric process A to C and then isochoric process C to D, we calculate for the final amount of Q. We already know that the internal change in internal energy is equal to 500 joules plus this amount of work done, 90 joules, for a total of 600 joules, representing the amount of heat that is absorbed by the system in changing from its initial state A to its final state D. Alright, so that ends our discussion for this video tutorial. Thank you very much for your indulgence.